G'day, in this video we'll be looking at quantitative applications of magnetism. This video covers dot points 4.3.3 and 5, focused on electricity and magnetism, and capping off inquiry question 3, which asks how do magnetized and magnetic objects interact. In this video we'll be starting to unpack the interactions of magnetic and magnetized objects through quantitative means. Effectively, we're going to be building our understanding of these two formulae here, which can describe the generation of a magnetic field. Specifically, magnetic fields which are produced by electrical currents in wires, or when we have lots of wires wrapped around together, a solenoid. So our learning intentions for today is to first introduce the measurement of magnetic field as well as the permeability of free space and look at their units of measurement. Then we'll be solving some problems which involve both of our formula that we're learning about in this video. And our key focus will be on magnetic fields produced around current carrying wire, as well as magnetic fields produced by solenoids. So first off, the magnetic field, it describes and quantifies the amount of force which is put on ferromagnetic or magnetized objects which are placed inside the field. Very similar in definition to an electric field or even a gravitational field. The pronumeral that you will see in formula for magnetic field is B, and the units of measurement is the Tesla, also shown with a capital T. Just for some scale and perspective, the Earth has a magnetic field. That's what allows us to use compasses, for example. The magnetic field of the Earth is actually quite small. It's about 30 to 60 microtesla. Really strong permanent magnets, like neodymium magnets, may have a magnitude around 1 Tesla. So even for a really strong magnetic field, the value or magnitude of the magnetic field in Tesla is not quite high. We can get up to, say, 100 Tesla, but that requires specialized lab equipment, which is being produced for very specific and specialized reasons. What that means is when we're doing quantitative processing for magnetic fields, we're generally working with values which are relatively quite small. The other value that's a little bit different today that we're going to be introducing is the permeability of free space. In the datasheet, it's referred to as the magnetic permeability constant, and it is equal to 4 pi times 10 to the negative 7. You will find that in both formula that we're using today, mu naught, or again, the permeability of free space, are both required to have these equations function. So our first formula here, B is equal to mu naught I over 2 pi r, can be used to calculate for the magnetic field which is produced around a current carrying wire. So B is a measurement of the field strength in Tesla. Mu, as we said before, is the permeability of free space and is found in your data sheet. But the two other variables, I and R, describe the two variables which impact the magnetic field strength observed when it's produced by a current carrying wire. So first off, the strength of the magnetic field is dependent on the current that is carried by the wire. If you have a higher current, you'll end up with a stronger or larger magnitude magnetic field. R, which stands for radius, describes the distance between the wire and the point where the magnetic field is being measured. As we've seen before for other fields, the strength of the field decreases as you get further and further away from the source of the field. So if the radius between where we're measuring the magnetic field and the wire that's producing the magnetic field increases, then we should expect to see the magnetic field observed reduce as a result. Let's just do a quick practice question to consolidate this concept. So if we have a copper wire which produces a magnetic field of 1.4 times 10 to the negative 4 Tesla at a distance of 7 centimeters from the wire, we're being asked to calculate the current carried by the wire. So I'm just going to draw a quick diagram first to give a visual of what this question is describing. So what I've drawn here is a wire which is coming out of the page. So I've used my dot and cross notation to be able to show that. So I've got a dot surrounded by a circle to denote that the current is moving out of the page. And using my right-hand grip rule, I've been able to draw a circle around the wire, which displays the direction of the magnetic field. Note that on any location in this circle, assuming that R is 0.07 meters in any direction, we should be able to measure the magnetic field B as 1.4 times 10 to the negative 4 Tesla. In concept, this is quite similar to diagrams that we've shown before with equipotentials when looking at electrostatics. Now for this question, we are being asked to calculate for the current that is being carried by the wire. Already we have the magnetic field. In our data sheet, we have our permeability of free space, and we also have R, our radius between the wire and the point at which we're measuring. So to solve for this problem, all we need to do is rearrange our equation to make I the subject, substitute, and solve. And the result that I've got here is 49 amps. This second equation that we're looking at today describes magnetic fields produced by solenoids. So again, we have the permeability of free space to work with. B is obviously the magnetic field strength produced by the solenoid. And our other three variables here are N, I, and L. N refers to the number of loops in the solenoid. So if you have wires that are stacked sort of on top of each other along in a coil, what we should be able to imagine is that each stacked part of the wire produces its own magnetic field. And so if you've got them stacked one on top of the other, each little circular magnetic field is going to add on top of the other, meaning that overall you end up producing a larger magnetic field as a whole when you have all of the loops working together to produce magnetic field. So in that case, if the number of loops in the solenoid were to increase, it would also increase the strength of the magnetic field produced by the solenoid. Again, we have I, the current carried by the wire, as a variable in this equation as well. If we have a higher current in the wire, that will mean that the magnetic field strength of the solenoid will increase as well. We also have the length of the coil. Essentially, the more spread out the wires are as they loop around to make our solenoid coil, the weaker the overall field that they'll produce. So a low length of coil will increase the magnetic field strength of the solenoid. In our practice question that we have up here, it says we have a solenoid which is 30 centimeters long and is producing a magnetic field of 0.23 Tesla. Now the question states if the current flowing through the solenoid is 2.9 amps, then we're to calculate the number of loops in the coil. So to give a little bit of a visual, we have a solenoid, which means that we have a wire which has been wrapped around in a series of loops, and the length of the solenoid is 30 centimeters. Additional information that we've been given is that inside the magnetic field is equal to 0.23 Tesla, and the current produced is 2.9 amps. Now we're being asked to find the number of loops in the coil, which in this case is N. So to figure out what N is, we'll need to rearrange our equation to make N the subject, substitute, and solve. Now, because the required magnetic field in this question is so high, and relatively speaking, the current is quite low considering the large number, the large magnitude of the magnetic field, it's actually going to require a very large number of loops in the coil to be able to achieve a magnetic field this high. In fact, it'll take about 19,000 loops in a 30 centimeter space for this magnetic field to actually be produced given the conditions that we have. Thank you very much, everyone. This video takes us to the end of Module 4 and, more largely speaking, the end of the Year 11 course. Thank you for your efforts getting through this Year 11 component of the course. In our following videos, we'll start to move into Module 5, the beginning of the Year 12 component of the course and beyond. Until then, have a good one.